In this topic, we will talk about torque converters and torque dividers. We will show how they are used in place of direct drive flywheel clutches to provide a fluid link between the engine and the transmission.
The standard torque converter delivers 100% of the engine's power to the transmission through a fluid coupling. Its benefit is that when a machine is heavily loaded, as in dozing or excavating work, it multiplies engine torque, sending higher torque to the transmission and greater force to the dozer blade or bucket. Thus, it greatly increases a machine's ability to power through rising loads.
Caterpillar uses torque converters in the power shift planetary and countershaft transmission, as well as the power shuttle transmission versions, to be covered later, that power the 950 through the 988 wheel loaders, plus the 910 wheel loader, the D5M and D6M track-type tractors, and the 416 through 446 backhoe loaders.
The torque converter's four main components are impeller, turbine, stator, and output shaft. The impeller is the converter's driving force. It is driven by the engine flywheel at engine speed and acts as a pump to direct the converter's oil to the turbine. Its curved vanes speed up the oil flow as it leaves the impeller. The turbine rotates from the force of the impeller-driven oil and turns the converter's output shaft. The turbine's output vanes are also curved to transmit as much of the fluid's power as possible through to the output shaft. The non-rotating stator is fixed to the converter housing. Its job is to redirect fluid flow from the turbine back toward the impeller. This increases the fluid speed, thus increasing the converter's output torque. The output shaft is splined to the turbine and sends power to the transmission. It connects to the transmission through a yoke and drive shaft, or directly to the transmission input gear.
The torque divider differs from a standard torque converter by the addition of a planetary gear set between the flywheel and converter. Transmissions with torque dividers are used in the D6 through the D11 track-type tractors. In this arrangement, the planetary gear set and converter connect to the same output shaft carrying power to the transmission. Under light loads, up to 30% of engine torque goes through a direct drive. As load increases, more engine power goes through the converter, multiplying torque to enable the machine to power through the increasing load. The torque converter direct drive is used in the 621 through the 657 scraper and uses both torque converter drive and direct drive, which are engaged sequentially as a vehicle's ground speed rises.
In first and second range, torque converter drive provides the high rim pull and hydraulic power for a scraper to pick up and eject a load, and to accelerate from load and dump areas. Reverse gear is also torque converter drive. In third through eighth ranges, a scraper automatically changes to direct drive for maximum efficiency. Modulated clutches assure shifts are smooth and properly timed.
The impeller clutch torque converter used in Cat 988 through 994 loaders lets the operator closely match rim pull to any operating condition. Using the left brake pedal, an operator can gradually reduce rim pull down to 20% and then brake to carefully inch up to a truck or hopper, or to change direction. The operator can also use a 4-position dial to set maximum rim pull in first gear at his choice of 80, 65, 50, or 35% to keep from slipping in wet or uncertain underfoot conditions. Lock-up torque converters combine the rim pull and smooth shifting of torque converter drive and the efficient performance of direct drive. It consists of a single-stage torque converter with a freewheeling stator equipped with a lock-up clutch. As the machine begins to move in first gear, the torque converter provides high rim pull for faster acceleration. When the machine reaches approximately 4.5 miles per hour, the lock-up clutch automatically engages, and the machine operates in direct drive while in all other gears. As the transmission shifts through the higher gears, the lock-up clutch releases and re-engages with each gear shift, protecting the powertrain from torque spikes while allowing smoother shifts and longer component life. Transmissions with lock-up torque converters are used in all Cat off-highway trucks, the 525B, 535B, and 545 wheel skidder, and the 24H motor grader. Engine power must be converted to useful power by controlling speed, direction, and force. Transmissions do this by either hydraulically engaged planetary clutches or hydrostatic hydraulic drive. Each of these methods has different characteristics for ground speed, torque, clutch maneuverability, and implement force. Direct drive transmissions use mechanical gear trains to control speed, direction, and power from the engine through the drivetrain. A direct drive transmission receives engine torque through a flywheel clutch that gradually engages the engine and transmission. The flywheel has three parts. The driving plate is splined to the transmission input shaft. The driven plate is splined to the driving plate, which also connects it to the transmission shaft. When it turns, the transmission shaft turns. The driving disc between the two plates is splined to the engine flywheel and rotates at engine speed. When the clutch is disengaged, the driving and driven plates are idle, with the driving disc rotating at engine RPM. When the operator shifts into a gear and engages the clutch, a cam link and sliding collar mechanism push the two plates together with driving disc between them. As friction increases, the engine power in the driving disc begins to rotate the plates, turning the transmission shaft. When fully engaged, the disc and plates rotate as a unit.
Speed changes are made by engaging gears of different sizes. When the driving gear is smaller than the driven gear, output speed is reduced and torque is increased. When the driving gear is larger than the driven gear, output speed is increased and torque is reduced. When gears are the same size, force is simply transferred from the driving to the driven gear with no change in speed or torque. To move from neutral to reverse requires engaging three gears: the driving gear, driven gear, and an idler gear. An idler gear is located between the driving gear, driven gear, and an idler gear. An idler gear is located between the driving and driven gear and is used to change the direction of the output shaft's rotation. If we want to move in reverse, we want the output shaft, to which the sleeve of the driven gear is splined, to turn the same direction in which the input shaft is turning.
Direct drive transmissions are used in work needing few gear changes. An example might be a Challenger ag tractor as it works in the fields. The advantages of direct drive transmission are low initial cost and low repair costs. Power shift transmissions change gears and speed under load, allowing full power speed and direction changes. Smooth shifting reduces operator fatigue in frequent shifting applications. Planetary power shift transmissions are made up of planetary gear sets that work similar to the way planets revolve around the sun. Any members of the planetary set, the sun gear, ring gear, or planet carrier, can be stopped by hydraulic clutches. When the clutches are disengaged, the sun, planet, and ring gears rotate as a unit. But when the clutches are engaged, they stop one of the members of the planetary set. Combining planetary gears into a power shift transmission provides the required number of gear ranges and forward-reverse speeds to match the machine application. The name countershaft power shift transmissions comes from adjacent shafts that run in opposite directions and counter each other. All gears are in constant mesh. Like power shifts, they can make speed changes under full load. Operator controls actuate speed clutches that connect various gears. Direction is changed the same way, using directional clutches. These are larger and contain more friction discs and clutch plates because of the higher energy they transmit during direct. The hybrid planet. The name countershaft power shift transmissions comes from adjacent shafts that run in opposite directions and counter each other. All gears are in constant mesh. Like power shifts, they can make speed changes under full load. Operator controls actuate speed clutches that connect various gears. Direction is changed the same way, using directional clutches. These are larger and contain more friction discs and clutch plates because of the higher energy they transmit during direction changes. The countershaft transmission has fewer parts than planetary transmissions, making repair and service faster and cheaper. The hybrid planetary countershaft transmission combines the high torque multiplication of the planetary transmission with the minimal shifting of the countershaft transmission.
It is used in the Challenger 65, 75, 85, and 95 ag tractors, and the 14H and 16H motor graders, machines whose work involves long operation in the same gear. During shifts, the clutch action is modulated independently for smooth, strong, efficient shifts that maintain power and momentum.
Transmission is ideal where maneuverability and hydraulic force are important, such as work involving tight turns, short travel segments, and high implement demand. Hydrostatic transmissions facilitate power turns, counter-rotation of track for spot turns, automatic speed control, and load compensation. The hydraulic flow may also be directed to run machine implements or auxiliary equipment. Because of these qualities, Caterpillar uses this type of transmission in the D3C, D4C, and D5C track-type tractors, the 902 through the 914 wheel loaders, and the 953, 963, and 973 track-type loaders. In hydrostatic transmissions, mechanical engine power is converted to hydraulic power. This hydraulic power is then converted back to mechanical power by a piston motor in the final drive of each wheel or track. Unlike other types of transmissions, hydrostatics have no mechanical drivetrain parts. The engine drive shaft provides power to drive two piston pumps and a gear pump. The piston pumps deliver a varying flow of oil to the piston motors that drive the wheels and control their speed. To turn the machine, pump flow to one motor is decreased, which slows its wheels and causes the machine to turn in the direction of the slower wheel. These pumps and motors are bidirectional to allow travel in both directions. The gear pump supplies oil needed to operate the system and dissipate heat. Cat 416 through 436 backhoe loaders, both 2- and 4-wheel versions, use power shuttle transmissions. This type of transmission is manually operated, is synchronized, has a 4-speed direct drive arrangement featuring constant mesh helical gears, and hydraulically shifted forward and reverse shuttle clutches. Direction and travel speeds can be changed on the go through all gears via electro-hydraulic forward and reverse shuttle clutches. A synchronizer assembly assures that the input shaft from the torque converter and the clutch plates are rotating at the same speed when engagement takes place. Gear changes are smooth without losing load-carrying force or ground speed. A freewheel clutch in the converter allows the stator to freewheel during high-speed, low-load situations such as roading. A large capacity torque converter applies engine power efficiently, and a low second gear ratio provides high rim pull for outstanding lugging ability. When power leaves a mechanical transmission through an output shaft or transfer gear, it must be turned 90 degrees to the steering clutches of a track-type tractor or the differential in a wheel-type machine. That 90-degree turn is performed by the bevel gear set. And in a wheel-type machine, the differential assures that the power is split appropriately to each driving wheel.
These bevel gear sets are made up of a bevel pinion gear that's driven by the drive shaft, and a bevel ring gear that meshes with the pinion gear. The ring gear, in turn, is mounted to the differential case on wheel machines, or the ring gear shaft on track machines. Because these gears transmit full machine power, the bevel pinion shaft is supported on preloaded tapered roller bearings, and both gears are checked to assure they are a perfectly matched mechanical pair before being assembled into a machine.
The bevel pinion shaft is splined to the drive shaft yoke assembly at one end on wheel-type machines and to the transfer gears at one end on track-type machines. The other end intersects with the ring gear at a 90-degree angle. The pinion shaft turns the ring gear that sends power to the steering clutches or differential. Bevel gear teeth are tapered in thickness and height for durability and proper fit. The bevel pinion shaft is supported by tapered roller bearings. Bevel gears must be precisely adjusted. The bearings are preloaded to maximize bearing life. The bevel ring gear is driven by the bevel pinion shaft and bolted to the differential case assembly on wheel-type machines and the ring gear shaft on track-type machines. It provides power to the differential or steering clutches. The ring gear has tapered teeth to mate with the pinion.
The standard differential in wheel-type machines provides a balance of power to the wheels and transfers power to the final drives. The main components are the differential case assembly, spider, pinion gears, and side gears.
The differential case assembly houses the components of the differential group. The bevel gear is bolted to this case assembly. The case assembly turns the spider and pinion gears that intersect with the side gears to turn the axle shafts. The differential case also provides support to the axle shafts. The spider serves as the mounting for the pinion gears and rotates with the differential case assembly. The pinion gears or spider gears ride on the spider shaft and transmit power from the differential case to the side gears and then to the axle shafts. There are 2 to 4 pinion gears mounted to the spider, depending on model. The pinion gears remain stationary except during a turn or during wheel slippage. When a machine is turned, the pinions walk around the side gears to permit the wheels to turn at different speeds. The side gears are splined to the axle shafts. The pinion gears drive the side gears, causing the axle shafts to turn. During a turn or wheel slippage, the side gears will rotate at a different speed than the pinion gears, allowing the axles to turn at different speeds. Differential action allows a machine to turn on firm ground with continuous equal torque being applied to both axles, even though the wheels are rotating at different speeds. If one wheel is slipping, all torque is delivered to that wheel, while the other receives none, and the machine is immobile. To overcome this, various types of locking differentials are used. Since wheel machines often work in slippery underfooting, some means must be used to avoid stalling when all torque is being sent to a spinning wheel. Locking differentials do this. They lock both halves of the axles together, delivering equal torque to the wheels. When both wheels are on solid ground, normal differential action returns. Three types of differentials are used in Cat machines: no spin, limited slip differential, differential lock. The limited slip differential, LSD, is a locking type differential designed to give equal power to both wheels under normal traction conditions. The benefit of limited slip differential is when one wheel loses traction, it transfers the lost power from the least tractive side to the side with the most traction. The limited slip differential is a direct replacement for a standard differential group. It replaces the differential case assembly and all its components. The no-spin differential is an automatic locking type differential that forces both wheels to turn at the same speed regardless of tractive conditions. It effectively locks the wheels together, sending up to 100% of the torque to the wheel with traction. During a turn, the outside wheel disengages and overruns. The no-spin can replace a standard differential because it fits into the standard differential case assembly. The differential lock system locks the differential, forcing both wheels to rotate together at the same speed at all times. There are two types of differential lock systems: jaw clutch differential lock and the multi-disc differential system. A foot pedal activates the jaw clutch differential. A switch in the cab activates the multi-disc differentials. We've seen how power is delivered from the bevel gears to the final drives by conventional axles and wheel-type machines. Another more unique system is the four-piece axle you see here. It consists of four major components: two axle shaft housings, a center housing, and an intermediate housing. The four-piece axle offers several benefits. The inboard brakes are located next to the differential on the low torque side of the final drive. In this location, the brakes require less braking force than brakes located outside of the final drives. The inboard location also protects them from dirt and debris. The independent front and rear brake circuits have separate piston-type accumulators that allow the machine to be stopped even with a dead engine. To assure cool running, the brakes are bathed in axle oil. Inboard brakes can be serviced without disassembling the final drive. Four-piece axles enjoy longer life with high-strength, large-diameter axle shafts on the high-torque side of the final drive. The four-piece axle is trunnion-mounted to oscillate plus or minus 13 degrees. Even in rugged terrain, all four wheels stay on the ground for stability and traction. The four-piece axle design is used in 13 models of integrated tool carriers, from the IT-12B through the IT-62G, and in 18 models of wheel loaders, from the 910E through the 970F. Steering is done by changing the angle of the wheels to the center line of the machine, right or left. The only part of steering involving the drivetrain is the differentials. Track-type machines are different. Track-type machines steer by manipulating the drivetrain, specifically by causing one track to turn faster than the other. Cat machines do this in one of three ways: hydrostatic drive turning, steering clutch, differential steering.
In hydrostatic drive track-type loaders, hydraulic piston motors drive each track. The speed and direction of each track is controlled by piston pumps that power the motors. This type steering is ideal for track-type loaders, which often have to maneuver in close quarters. It is extremely versatile, making possible any degree of turn, from gradual to spot turns, made possible by actually reversing the direction of the track.
The steering clutch system turns a track-type tractor by using a clutch to interrupt the flow of power to one track while the other continues driving. To turn the machine, the operator uses a fingertip control lever whose first movement disengages a hydraulic steering clutch, causing a gradual turn. Moving the lever further engages a spring-applied steering brake, causing the machine to make a sharper turn. There is one control lever and one clutch and brake for each side of track. The clutch and brake assembly are located on the bevel gear shaft between the bevel gear and final drives. Because power is partially interrupted using this system, turns cannot be made under full power. The steering clutches are engaged by hydraulic pressure, but the brakes are engaged with spring force and must be disengaged hydraulically. Therefore, if hydraulic pressure is lost, spring force engages both brakes, stopping the machine. A single separate foot brake pedal that applies both brakes simultaneously controls normal machine braking. The third system, called differential steering, uses 3 planetary gear sets and a hydraulic motor to change the speed of each track. This system delivers full, uninterrupted power to both tracks during turns. Power from the transmission is delivered through the bevel gears to 3 planetary gear sets, then to the final drives and tracks. By adding power to one of the planetary gear sets, the motor increases the speed of one track and equally decreases the speed of the other. Thus, the hydraulic motor determines the direction and degree of the turn. The results are turns of any degree from slight to sharp with no interruption in power. The operator turns, reverses direction, and changes speed ranges using one hand on a single tiller. This Caterpillar patented steering system is available in the Caterpillar D6R through D9R.
Service
Brakes are the components that slow, stop, or hold a machine stationary. On Cat machines, service brakes are located at the wheels of wheel-type machines. In track-type machines, they are located on the axle shafts. Brakes usually work by pressing a non-rotating surface against a rotating surface. The resulting friction stops the machine. At the point where the 2 rotating surfaces meet, the inertial force of the machine is sometimes converted into bake oven heat. Just another reason why balanced component wear life is important to machine performance. The braking requirements of various types of machines differ, chiefly because of the differences in the work they do. To ensure each machine has the braking system it needs, Caterpillar has 4 types of service brake: expanding shoe, caliper disc, wet disc, expander tube. The expanding shoe brake system is very similar to that found on the rear wheels of automobiles. It uses 2 curved brake shoe assemblies per wheel that expand internally against a metal drum. The brake shoes, when actuated, are forced against the cylindrical drum that rotates with the wheel. Expanding shoe-type brakes are adjustable to compensate for lining wear. Expanding shoe-type brakes are becoming less common because they represent old technology and cost more to service. However, they are still used on some scrapers, wheel loaders, motor graders, and wheel dozers compactors. The design of the caliper disc is very similar to that found on the front wheels of automobiles. It consists of a rotating steel disc located between caliper linings. The brake system pressure forces a piston against the metal plate of the lining assembly, compressing the friction material, brake pad, into the rotating steel disc, producing a braking action.
Let's take an inside look at how the oil-cooled hydraulic brakes work. The wheel axle and the outside ring enclose the brake discs. The multiple disc system consists of alternating brake discs and spacer plates. The spacer plates have splines only on the outside edge. The splines fit into the teeth in the outside ring, allowing the plates to move back and forth, but not rotate. The actual brake discs, indicated by the crosshatch design, are just the opposite. They have splines only on the inside and attached to the teeth on the inside hub. The brake discs rotate with the wheel axle and also slide back and forth. The complete brake system is built with multiple disc and spacer pairs, each disc rotating with the axle, while each of the spacer plates is held stationary by the outer ring. During operation, cooling oil runs throughout the system and in between each of the discs and plates. Braking activity is controlled by hydraulic pressure. The primary piston is controlled by the hydraulic pressure here and the secondary piston here. During normal machine operation, the secondary spring-activated piston is held in place by high-pressure hydraulic oil. The primary piston is held in place by a combination of retract springs and a slack adjuster. When regular braking is applied, the hydraulic oil behind the primary piston pressurizes. As the pressure increases, the primary piston moves, forcing the spacer plates together and restricting the rotation of the alternating brake discs. When the brake is released, the oil pressure drops and oil begins draining from the piston cavity. The retract springs pull back the piston to a seating determined by the slack adjuster, releasing the pressure on the brake discs. When the parking brake is applied, or hydraulic system pressure is lost, the constant high pressure in the lower cavity is released. The big spring activates the secondary piston. This action moves both pistons, forcing the discs together and restricting rotation. The hydraulic oil that cools the brake system enters here. It circulates throughout the braking system. Oil fills the crosshatch grooves in the brake discs, creating an oil film that prevents direct contact between the discs. The shearing action of the oil absorbs the rotational energy and carries heat away, causing the vehicle to stop or slow. With no direct contact between rotating surfaces, brake life is extended significantly. The cooling oil exits the system here.
Expander tube brakes consist of a series of brake blocks mounted on the outside of an expandable tube. When the tube, or bladder, is hydraulically inflated, the friction blocks are forced against a rotating brake drum. Expander tubes are used in older model wheel loaders and early design wheel tractors and compactors. Final drives apply driving force to the wheels or tracks. The final drives of a wheel loader and the final drives of a track-type tractor are different, but they perform the same function. They reduce rotating speed and increase torque. In fact, this is where the greatest torque rise occurs, in the gears. The components ahead of the final drives are smaller and lighter because they carry less torque than the components after the final drive. There are four types of final drives used in Cat machines: bull gear single reduction, bull gear double reduction, planetary single reduction, planetary double reduction. The single reduction bull gear consists of a single pinion gear that receives power from the steering clutch, driving a large bull gear that in turn is fastened to the drive sprocket of a track-type machine. The difference in size of the two gears provides up to a 6-to-1 speed reduction and up to 6 times torque increase. The bull gear single reduction final drive is used in small track-type tractors and Challenger Ag tractor models 65 through 95. Oval track machines need greater speed reduction and more torque to handle larger loads. In these cases, a double reduction bull gear drive is used. A double reduction final drive has an input shaft that, through a pinion gear, rotates the first bull gear. From this first bull gear, an idler shaft turns a second pinion gear that in turn drives the second bull gear. The output shaft extends out from the second bull gear. The first reduction of up to 4-to-1 occurs between the pinion gear and idler shaft gear. The second reduction of up to 4.3-to-1 takes place between the idler shaft pinion and bull gear that is fastened to the sprocket. Double reduction can increase torque up to 17.2 times. The single-reduction planetary final drive consists of a planetary gear set that includes a sun gear, ring gear, planet gears, planet carrier, planet shafts, and bearings. The ring gear is stationary and attaches to the axle housing on wheel-type machines and to the spindle housing on track-type machines. The sun gear receives power from the axle shafts to drive the planet gears. The planet gears revolve around the inside of the stationary ring gear, transmitting torque to the wheel assembly or sprocket. Single-reduction planetaries can reduce speed in the 4.5 through 9.5 to 1 range and increase torque as much as 4.5 to 9.5 times. They are used in small track-type tractors, medium wheel loaders, scrapers, small excavators, and the 777 and smaller off-highway trucks. A double-reduction planetary final drive contains 2 planetary gear sets. Both planetary sets in this final drive share a common fixed ring gear. In some cases, this ring gear consists of 2 connected pieces. The stationary ring gear is attached to the axle housing on wheel machines and the spindle on track-type machines. The planet carrier of the first set drives the sun gear of the second set. This forces the planet gears of the second set to walk around the inside of the fixed ring gear, causing the planet carrier to drive the sprocket or wheel hub, moving the machine.
Double-reduction planetary final drives can reduce speed in the 10 through 22.5 to 1 range and increase torque by 10 to as much as 22.5 times. They are used in large track-type tractors from the D7 to the D11, large wheel loaders such as the 994, and large off-highway trucks from the 785 up.